Good day everyone, I am General C. Acero, taking up Bachelor of Secondary Education major in Science. So together with my partner Rachel P. Gores, we will be going to report about photoelectric effect cannot be explained by classical physics. But first, let us know what is photoelectric effect. What is photoelectric effect? The photoelectric effect is a phenomenon in which electrons are ejected from the surface of a metal when light is incident on it. These ejected electrons are called photoelectrons. So the process through which photoelectrons are ejected from the surface of the metal due to the action of light is commonly referred to as photoemission. The photoelectric effect occurs because the electrons at the surface of the metal tend to absorb energy from the incident light and use it to overcome the attractive forces that bind them to the metallic nuclei. So the photoelectric effect cannot be explained by classical physics because of the following factors. First is the absence of lag time. When radiation strikes the target material in the electrode, electrons are emitted almost instantaneously, even at very low intensities of incident radiation. This absence of lag time contradicts our understanding based on classical physics. So classical physics predicts that for a low energy radiation, it would take significant time before irradiated electrons could gain sufficient energy to leave the electrode surface. However, such an energy buildup is not observed. So the second one is the dependence of kinetic energy of photoelectron on the intensity of the incident radiation. So typical experimental curves are shown in figure 6.3.2, in which photocurrent is plotted versus the applied potential difference between the electrodes. So for the positive potential difference, the current steadily grows until it reaches a plateau. Furthering the potential increase beyond this point does not increase the photocurrent at all. A higher intensity of radiation produces a higher value of photocurrent.
Good day, ma'am. Good day, classmate. I am Rachel P. Gores, and I will be the one to continue the report of Ms. Acero, the photoelectric effect. Why photoelectric effect cannot be explained by classical physics because of these following factors. So as the continuation, I'll be the one to continue the dependence of kinetic energy of photoelectrons on the intensity of the incident radiation. So for the negative potential difference, as the absolute value of the potential difference increases, the value of photocurrent decreases and becomes zero at the stopping potential. For any intensity of incident radiation, whether the intensity is high or low, the value of the stopping potential always stays at one value. In the photoelectric effect, the kinetic energy of photoelectron is independent of the intensity of incident radiation and depend on the frequency of the incident radiation. So the presence of a cutoff frequency. For any metal surface, there is a minimum frequency of the incident radiation, so below which a photocurrent does not occur. The value of this cutoff frequency for the photoelectric effect is a physical property of the metal. So different materials have different value of a cutoff frequency. None of these observed phenomena is in accord with the classical. So as you can see in the picture, kinetic energy of photoelectrons at the surface versus the frequency of the incident radiation. The photoelectric effect can only occur above the cutoff frequency. Measurements for all metal surface give linear plots with one slope. Each metal surface has its own cutoff frequency. The presence of a cutoff frequency. So according to the classical description, the kinetic energy of photoelectrons should not depend on the frequency of incident radiation at all, and there should be no cutoff frequency. Instead, radiation at all. So instead, in the classical picture, electrons receive energy from the incident electromagnetic wave in a continuous way. and the amount of energy they receive depends only on the intensity of the incident light and nothing else. So in the classical understanding, as long as the light is shining, the photoelectric effect is expected to continue.